very much, if you like very much at these distributions, we can take some functions of them, and then we can still do some good work. And here there is, it is usually called a dichotomy. If we have a random variable and its distribution function, and all moments are finite, there are only two possibilities. Either X or F is moment determinate, or we say unique with these moments, and this is the abbreviation, or it is moment. So, is there some question to me?
No, I just cut it, the microphone of some persons.
Ah, somebody.
I'm sorry.
Disturb us. No, it's okay. So the other possibility is the distribution and the random variable to be moment indeterminate, M in that. So M in that, it is a phenomenon. So we need to understand this a little bit better. And here is a fundamental result, which is a qualitative result, that if we have F, which is M in that, then there are infinitely many distributions of any kind. And you can see here, absolutely continuous, discrete, or even singular. And all have the same moments as F. So Christian Berg is a famous mathematician from Copenhagen, and he's the author of one of these great papers which appeared in the Arab Journal of Mathematical Sciences. And here I'm recording the names of the moment problem. Hausdorff, if it is bounded interval, we take 0, 1. Stiltes on 0, infinity, and Hamburger on the whole real line. Now we can ask at this general question, so why the moments? Okay, we can tell it why not. The moments are very simple characteristics of any distribution, of any random variable. Now, if we remember the notion called characteristic function and the so-called inversion formula, we know that we can write it in the characteristic function. Now I'm showing it here. And if we know the moments, of course, under some condition, additional condition, that this function must be analytic around 0. So then, knowing the moments, we can recover by the inversion formula, we can recover the distribution function. And we can do the same job by using the moment generating function. Now I'm showing it here with my mouse. Sometimes this is called Cramer condition, and it is strong if T0 is infinity. And there is a very easy way, if we know the moment generating function or the characteristic function, to calculate the moments. So you differentiate, you substitute the argument T equals 0, and you produce the moments. And here there is a question now based on this so-called theoretical moments or on the empirical moments obtained maybe from some huge data set, can we obtain or identify or recognize F? And so these kind of questions, they have answer either yes or no. And because of the importance of both determinacy or uniqueness and indeterminacy, non-uniqueness, we can ask it even at this stage, what is the main reason for some distribution to be non-unique in terms of the moments? And a quite easy explanation is to tell that the moments start growing very fast. So n is the order of the moment, and so very fast that we will see a little bit later. And it turns out that there is a boundary until which we still have uniqueness, and if the growth of the moments is more than, for example, this is the even order moment in the Hamburger case, it is on the whole real line, the moment of order 2n, here there is some constant, but this is the behavior, right? So 2n factorial. And on 0 infinity, the Stiltes case, mn itself, the largest rate of growing to keep the uniqueness is 2n factorial. And we will see a little later why exactly these numbers. And also we can, in other terms, we can give conditions by looking at what is called the tail of the distribution f. There are either two tails or one tail. So heavy tail is a distribution without moment generating function. So this is equal infinity. And just in a few minutes, we will see cases when we have exactly this. And now I will show to your attention a very simple example involving our favorite normal distribution and also another distribution which is quite easy. It is even discrete. So this example is both, it's warming and warning. And now you will see why it is so. And so we have all the notations here. So mu3 is 3, and here one bracket is missing, and don't pay attention. In probability and statistics, we introduced two coefficients, which are called skewness and kurtosis, and we can tell something about the shape of the distribution of the random variable or the distribution itself. It is well known that for the standard normal distribution, beta 1 is 0 because moment of order 3 is 0, and beta 2 is 3 because the moment of order 4 is equal to 3, and the variance is 1. And now the very natural question is n the only distribution with this skewness and kurtosis? And the answer is no. And we can give a very easy illustration. We take a discrete random variable x. Look, now plus minus square root of 3 and 0. It is symmetric with respect to 0. And these probabilities, the masses on plus and minus square root of 3 are the same. So we have good symmetric case. These are the first moments. And so this is 0 and this is 3. We notice something about the moments of higher order for x and also for z. But so we see that there are different distributions, different from the standard normal, with the same skewness 0 and kurtosis 3. So which means that we cannot characterize the normal distribution by these two coefficients. There are too many, and here there is another example by involving gamma distribution. It is double gamma on the whole real line. And so we have the absolute value modulus of x. And it turns out that there is it's interesting, it's a matter of calculation. We can calculate all moments are finite. We calculate the first 4 moments, and we find that with this value of the parameter a, now I'm showing, we have exactly skewness 0 and kurtosis 3. So it is another topic about the role of the skewness and kurtosis. But even from this example, we see that somehow we have to be very careful when dealing with the moments and eventually trying to make some conclusion about the kind or the shape of the distribution. And here is another reason why uniqueness or MDET property is so important. And we have to go 150 years back to the times of Chebyshev and Markov. And so these famous Russian mathematicians, they were living in St. Petersburg. So they proved for the first time the central limit theorem for quite arbitrary sequence of random variables. So here are some standard notations. So what Chebyshev was a master, and he is known for the so-called Chebyshev inequalities. Not only the inequality we use in probability theory, but also there are some integral inequalities, and they are exactly used to show that and Chebyshev was trying to calculate it. The moment of order 2k minus 1, this is the odd order moment of this quantity, standardized centered and standardized quantity. And he was showing that it converges to 0 when n goes to infinity. And the moment of order 2k goes to this very nice number. So we have this very interesting combinatorial sequence. So the odd are zeros and the even order are the so-called double factorial. However, so they notice that the limits are exactly the moments of this random variable, the standard normal. And then Chebyshev and Markov were the first to show by using, it is historically even interesting, they use the continued fractions to show that the normal distribution is the only one with these moments. So this, and this. And this is how they concluded that in our modern notations, the weak convergence. So Fn is the distribution function of this. And capital phi is the distribution function of Z. Of course, later we have some other great developments, Lyapunov and Lindeberg and Levy, Feller, etc. And a little bit later, I think it was 1931-32, these two mathematicians, Fréchet and Chohat, they proved a very general result which plays a fundamental role, not only probability theory, but also in analysis and in other specific areas. Even some people suggest to call this Chebyshev-Markov-Fréchet-Chohat theorem. Okay, we can do this. Now we have a sequence of distribution functions. They have all finite moments. And we have the convergence I'm showing now. So for any fixed n, we have, for any fixed k, we have convergence in n. And then it turns out that the limiting numbers, this mk, are, these numbers form the moment sequence of some distribution function denoted by f star. And then this important condition, if f star is moment determinate, then we have the weak convergence. And this theorem has so many applications in so many sub-areas. And I'm glad that one of the participants in our seminar today is Professor Yassin, and he's a master and great contributor exactly to random matrices. And I'm sure that he's smiling at the moment by mentioning his name. It is a good reason. Now I will just mention briefly, and on one page, I succeeded to locate the so-called criteria which are necessary and sufficient for the uniqueness. So these are classical criteria, classical conditions, but I call them non-checkable. They look very compactly, and I will make a few comments. These are, it's a very deep and beautiful mathematics. However, to check any of these practically is not possible. So we start at this x and f, or mu is the measure generated by f. People in analysis they like this. So this is the moment sequence. And now we start dealing with what is called Hankel matrices. So this is the basic Hankel matrix, and this is the shifted by one. So the shifted matrix is based on the moments. So starting from exactly M1 in the left top corner. Or in other words, these are the moments of the measure mu1. There is a name even of this, of the distribution here, F1, we put again. But so any of these matrices has, if there is an index n, there are n+1 non-negative eigenvalues, and there is one eigenvalue, which is the smallest. So when n goes to infinity, all the eigenvalues, including the smallest, they decrease monotonically. So this is for the basic and also for the shifted Hankel matrix. And now I will use it. Is there a question to me? Okay, I will continue. Now I will use it. It is better to use now H det and HM in det and respectively S det, S in det. H is for Hamburger, S is for Stiltes. And now first the Hamburger case. And I put here one very basic, very important, relatively recent paper, only 20, 21 years ago. So mu is unique, so it is on the covariant line, if and only if the minimal or the smallest eigenvalues goes to 0. So, and because it is equivalent, it is non-unique or moment indeterminate if going down, there is a strictly positive limit. And this C0s, this can be calculated by using some orthogonal polynomials, etc. But this is it's a beautiful mathematics, but it is not directly related to our goals today. And in the Stiltes case, it turns out it is a little bit more complicated. So mu is non-unique if and only if these two measures, this and this, are non-unique. And this is equivalent to so the smallest eigenvalue of Hn converges to strictly positive limit. And for example, and also this smallest eigenvalue of the shifted goes to another positive. And this these limits can be calculated. And here there is another formulation. Now I will turn and I will show this non-checkable. And this means that you can expect something which is checkable or verifiable. And I tried and I succeeded to put on one page the conditions which are known in the literature. They are used by many people wishing and needing to do this. And the first is, it's called Cramer condition or analytic characteristic function. So existing moment generating function. And so the next is for positive random variables, the so-called Hardy condition. So because x is positive, square root of x is well defined. And now, in fact, we need now Cramer for the square root of x. But the conclusion is for x. Now, very popular and well-known is the so-called Karleman condition, which is given here. This is on the whole line Hamburger case. We involve moments of order 2k, so even order moments. And this is, we involve all moments, mk, in the Stiltes case, because all these moments are positive. And here, of course, we avoid the zeros. if this happens. Now there is a result which is converse Kahneman. What will happen if C is less than infinity? And it turns out that if we add one additional condition on the density, we can derive the non-uniqueness. Now, there is another condition which is called Crane condition. It is exactly now I'm showing, and so this is the result of Crane. This is how his name is pronounced, and this is a condition which is sufficient for the non-uniqueness. So what I'm now showing, this is in the hamburger case, and this is in the Stiltes case. This A is some small positive number in order to avoid some singularity near zero. And now, if asking, like with the Kahneman, but what will happen if this Crane quantity is equal infinity? And this is already a result of good mathematician from Taiwan, Godong Lin. And he suggested one very simple additional condition. So this condition here. So, but however, we need not only the density to exist and to be positive, but also we need the derivative of the density. And under so this condition plus this condition, they imply uniqueness. And now there is another condition which is more recent. It is called to use the delta rate of growing of the moments. We take this ratio of two neighboring moments, mk plus 1 over mk. This is in the Stiltes case, and in the hamburger case, we are working with the even order moments. And it turns out that here, this can be explained, that for large k, so this is there is a constant and k power delta, where this delta is non-negative, but it could be also plus infinity. And here there is a quite useful result, which is this bullet. If delta is less or equal to, in both cases, S and H, we have uniqueness. However, if delta is more than 2, and this Lin condition is satisfied, which is Lin condition is satisfied practically for any good distribution, continuous at the density. And so very fast rate of growing of the moments, a Lin condition taken together implies non-uniqueness. And also there is something which is called Stiltes classes. This is a class infinite family of distributions around any distribution which is non-unique, and we will give good illustration now. As I included into the short abstract of my talk, let us do this job with one of our favorite distributions. This is the normal distribution. So we use it in the standard notation Z. And now we are interested in the so-called Cox transformations. The square, power 3, power 4, any power, R. So because Z has a moment generating functions, Cramer, and so it is unique. Now, the absolute value of Z, so this is already the so-called half normal. It is also Cramer. But also this means that Z square satisfies Hardy condition. So we are using Cramer and Hardy, and this is how we derive that, for example, power 4 of this standard normal random variable is unique. And this is, look at, this is the shortest, the most compact, and in my opinion, the most beautiful proof that power 4 of the standard normal random variable is moment determinate or unique. Of course, here I mentioned that Z square, this is chi square with 1 degree of freedom. So there is an analytic moment generating function, so we can go also this way. And this is the comment that I just made. Now we can prove in a few different ways this result that in absolute value, for any R, any power between 0 and 4, we have uniqueness, and we have non-uniqueness from any power more than 4. Now you have seen, and you could stop me and tell it, Jordan, you missed power 3, and I will tell you immediately, no, I didn't miss, but I was keeping this for a little later, and I will tell you all the details, because this case is very strange. So now this is by X, we denote Z power 3. So this is the density of X. And there are a few different ways. We can use it a crane and show this is only one way. And there are a few different ways to show that this is non-unique. And however, on this line, I'm showing now, I have written 2 things which are a little bit strange. And so X itself is non-unique. However, in absolute value, we take the absolute value and it is unique. And you can stop here and try it and wait a moment. But why this happens? And here is the explanation. So X, this X, like Z itself, is on the whole real line. This is a hamburger case. We calculate the rate delta, and it turns out the rate delta is 3. And 3 is more than 2. And the Lin condition is satisfied trivially, or it's in 2 lines, of course, to check. And this is how we conclude the non-uniqueness of the cube of power 3 of Z. Now we take the absolute value. Now this is on 0 infinity, still this case. We calculate the moments. We use it in some explicit expressions by using gamma function. And it turns out that now the rate is 1.5, which is less than 2. And we have uniqueness. And now here is another way, as I mentioned to you, I use the name Stiltes class. And now I will write this infinite family of functions. So this G I'm throwing, it is this G. This H is called perturbation. It is here. The perturbation has a norm 1. So the values are between -1 and 1. And I'm involving here a small parameter epsilon running between -1 and 1. And we can show that so G epsilon is a probability density, and all the moments of random variable, maybe some, say, X index epsilon, all these have the same moments as X. And now we turn to another distribution, which is also among the favorite distributions. This is the log normal. Just to avoid everything to be clear, I have written all the details. So Z is our standard normal, and X now is the exponential transformation. And here is the density. X is strictly positive. There is no moment generating function, so we have heavy tail. So we cannot use Cramer, we cannot use Hardy. However, strangely enough, we write the moments, so we multiply here by X, small x power k, integral from 0 to infinity. And after some work, these are maybe 3-4 lines, some change of variables, and we find that all moments are finite. And look, so beautiful formulas for the moments of the log normal random variable. And now, sometime I'm telling just from the sky. I'm taking from the sky and I'm writing two infinite families. One is this X index epsilon with a density F epsilon. So F, this F is this F. And previously we had the function H, now it is this specific function, the perturbation. And now I will write another family, which is purely discrete. Now we have Y index A. A is any real number in parameter. So these are the values, and these are the masses. So this capital A is a normalizing constant. So the sum of all these masses is 1 now. And this is, according to some people, a shocking property. We calculate the moment of order k of X epsilon by using this density. We calculate the moment of order k of the random variable YA, given here, and it turns out that the moment of order k is the same and is equal to this beautiful number. So the conclusion is obvious. The log normal distribution or the log normal random variable are non-unique in terms of the moments. So many. And what we have here is another illustration of the non-uniqueness. So we have one illustration by using a continuous, or if you wish, absolutely continuous Stiltes class. And this here, now I'm showing, this is a purely discrete Stiltes class. Now, the Kahneman condition plays a great role. If asking anybody, maybe if asking you, do you know some good condition guaranteeing the moment uniqueness? Usually the people tell the Kahneman condition. So, however, we can ask it, but how does this Kahneman imply the uniqueness? And there are a few ways to do this. I personally like very much the so-called method of metric distances. It goes back to Zolotarev or Zolotarev, and this is my former student, and he was a PhD student of Zolotarev. In the set of distribution functions, we introduce some appropriate metric. We can take Levy or Kolmogorov uniform metric or another. So we have symmetry and we have triangle inequality. And we have this very important, very simple, very natural, that the distance between f and g is 0 if and only if f is equal to g. And here's a result of another mathematician from St. Petersburg, Lev Klebanov. Now he's in Prague, the Czech Republic. And his result is the following. If we take f and g, having the same, okay, all moments are finite, but they moment up to order 2n coincide. And now we denote by Cn the beginning of the Kahneman series. So we take k from 1 to n. So all these are finite. And what Klebanov and his co-authors proved quite long ago is that there is an upper bound, some constant, quite easy. And in the numerator, we have the logarithmic function, and this Cn minus 1, and then here we have the power. Now, what I'm showing, this is exactly the Kahneman condition. So if the Kahneman series is divergent, then we have uniqueness. But if this is equal to infinity, then this Cn will converge to plus infinity. And since the logarithmic function is growing very slowly compared with the denominator, the power of this, then we have that this goes to 0. And this 0 corresponds to f equal g. So this is how to show how to tell it or how to explain why Kahneman implies uniqueness. And now I will tell you about a few new checkable conditions for M determinacy. So one of them is, I'm repeating here the classical crane. So this crane is the classical crane, and this is a little later, somebody else did. And the opposite result was done by Lin. Now, this requirement, now I'm showing the Lin condition. But there is a question, okay, now what to do if the density is not smooth, if there is, for example, there is no derivative. And now you will see the answer, sorry, you will see now one possible answer. And now, so we have to work with both the crane condition and the Lin condition. So what we have done is, it's a joint work by me and he's my former student, Peter Kopanov, and this is L is for Lin. Lin, the same Godong Lin. So we make a little bit stronger the crane condition and a little weaker Lin condition. So here we add something more. In the original crane condition, we have this 1 plus x square. X square or 1 plus x square not important because we can move a little from neighborhood of 0. However, we need this slowly varying function logarithm x in the denominator. However, now the positivity of the density is enough for us, and also in order the logarithmic function to be well defined, and because for large x, fx goes to 0, we need this minus, the logarithm minus minus. So, but this is now, this will go to, now we require this to go to plus infinity. And for us, both at this condition and this condition, they can be checked, they can be verified. So this is because we call this new checkable conditions. So the statement is that this condition plus this condition imply uniqueness of the distribution F. And we have similar in the still test case, we use this condition and this condition is the same. Right? So only now here the crane quantity or the crane, it is called also logarithmic integral or so. And now most of our attention until now was devoted to absolutely continuous or continuous distributions. And now let us tell something about discrete. Actually, we have met already this example. You remember this Stiltes class, this discrete Stiltes class for the log normal distribution. So we have already one example. And now, in general, any discrete random variable is described by a pair, the set of values, V is for values, and this calligraphic P is for the probability distribution. So if discrete, we have finite or infinite, but these are real numbers. It does matter, you start from 0 or you start from 1, but you can order it. It is an ordered set in the Stiltes case and then in the Hamburger case. So all the masses are strictly positive. And of course, the sum of the masses is 1. And now we need a result of Henrik Pedersen. Pedersen is a former PhD student of Christian Berg. So this is the same great Berg. And what is here is an analog of the crane condition. So now we have this summation. And if this infinite series is finite this is sufficient for the discrete random variable x to be m indeterminate or non-unique in terms of the moments. And now we have the same question, but what can we say if this sum is equal infinity? And it turns out that we can give the answer in both cases, Stilte's case and Hamburger case. So now the set of values is n0. Okay, we go a little bit further. You can take it n0, we say 3 or 5 if you like, to avoid some logarithm of 0, etc. This is the values of x at near 0, they are not so important. So now we have this condition, which is the converse, which is a converse discrete crane, and this is analog of the Lin condition. And so if this and these conditions are satisfied, then we have uniqueness. And in the Hamburger case, when the values are okay plus minus, and the distribution is symmetric, this can be a little bit weakened, but I'm not going to talk. So we have again, so this condition is an analog. It is a crane condition. It is a discrete crane in Hamburger case, and this is analog of Lin. And under these two conditions, this and this, we have again uniqueness. And it was very interesting because for several years, I was disturbing at my friend and co-author, Godong Lin. And I was asking Godong, but what is Lin condition in the discrete case? And he was always telling, I don't know, I don't know, I don't know. And only after finding this condition, let me see, only after finding this condition in the continuous case, we got the idea how to write Lin condition in the discrete case. And so now we have this. And now let me tell you, I'm sure that behind normal, log normal, and exponential distribution we like very much, for example, the Poisson distribution, and here is an interesting situation. So this is Poisson random variable standard. So these are the values, and this is the collection of the Poisson masses, Poisson probabilities. There is a moment generating function and everything is okay. We have uniqueness. So all moments are finite and we have uniqueness. And now we are interested in what is called Box-Cox transformations, in particular the power transformations of the Poisson random variable. And it turns out, but also we can take the exponential transformation. And now here we have running power R. It is any real number. If you want, you can take, for example, R equal 2 or 3, or maybe any real, and we can give the answer. And it turns out, so this was above it, X, this is itself the Poisson random variable, it is unique. However, and then we make one step, X square, so here the values are 0 square, 1 square, 2 square, etc., all the squares. And this is how I have denoted my set of values V. And the probabilities, the masses are the same, but the values are different. And it turns out that the square is still good. And here our Hardy condition is helping to show in a short and beautiful way that the square of a Poisson random variable is unique. And it turns out, if we take a little larger power, starting from power 3, 4, etc., we have already non-uniqueness. If we have, if we take it to the exponential, this is the way that I symbolically I have written the new set value, but the probability are the same. We have non-uniqueness. If you wish, you can see some details, the main details about this case. Okay, it was mentioned about my book at the counterexamples in probability. Some details can be seen at, in this book. And now a few words about another distribution, the exponential. It is very easy. This is the density. We have moment generating function, Cramer, Hardy. Now we take, for example, power 3. Power 3, it turns out, is non-unique. So this is the density, and the Crane criterion helps us to show this immediately. The moments we see, they grow very fast. If this was 2k factorial, then we have uniqueness. But 2k factorial is for the square. So the square of the exponential is unique. However, power 3 is non-unique. And here we have the explicit Stiltes class. And here I'm trying, so this G is this G, and this H is the function sign, with small shifting of the argument. Now, I want to involve another important property. This is infinite divisibility. So I claim that G itself is infinitely divisible. This more or less is known in the literature. However, G epsilon is not. And here there is an open question. We know from the fundamental result at the beginning that if we have something which is non-unique, then there are infinitely many continuous, but also infinitely many discrete. And your speaker today does not know any discrete random variable such that the moments are 3k factorial. I know that, that there are, and even there are infinitely many. So we have to write this infinite system. So these are the unknown. There are, okay, too many unknowns. So these are unknown, and these are unknown. The sum is 1. Okay, I don't know it, how to do this. I will be very happy if somebody is able to help. And we can do something similar also with power 3 of the normal random variable. We spent some, we paid attention to this power 3 before. We can write the density, and we know the perturbation. And here, once again, the center F, center is if epsilon is 0. So the center F is infinitely divisible, and my claim is that any other is not infinitely divisible. And also, like in the case of exponential, we are looking for a discrete random variable on the whole real line. And so but now here you can see the moments of power 3, so the moments of this. So zeros, the odd, and if you take this at z power 3 or power 2 k, so these are the moments. I don't know. And here there is something else about involving another property, which is called unimodality. Some people found that it is a very beautiful question, but it turns out that it is quite difficult. And here there is something which involves a property about the Levy measure of a function which is infinitely divisible with all moments finite. So it is known that then F and L, they have, if F has all moments finite, then the same is true for L. And now this is the conjecture that F is unique if and only if L is unique. There is a partial answer, but not completely. And now just a few moments, a few short comments. in one talk, and I can see that my time is almost over. We have some quite interesting results about random sums. And so these are sums of, so the number of the terms we are summing is random. So these are random sums. Then there are quite interesting results about the products of random variables. Some functionals of random variables or of stochastic processes, including the so-called exponential functionals used at maybe in financial mathematics. And it is another topic that I have given talks about multivariate distributions. And then another topic is to work in terms of the cumulants, or to follow the so-called maximum entropy approach. And so the moments are used at a quite intensively in statistical inference problems, starting from Carl Pearson, the British statistician. So this is the year when, or maybe 94, sorry, I think it's 94. And then later, Fisher. However, now there is something which is quite interesting. It is more recent result in the 1990s, that there is a very large class of exponential family of distributions. And for them, the maximum likelihood estimators, they coincide with the estimators obtained by the method of moments. So this is quite, there are the advantages and disadvantages of both. And I'm not going to talk about using moments in stochastic financial models. And there are several modern areas I mentioned about random matrices, but this is perhaps a topic for in other presentations. Maybe not one, even a few, or even for maybe a mini course on this topic. So thank you for not only organizing this talk online, but also for your joining, for your participation, and thank you for listening to me. I hope very much that at least something, let me tell this way, there will be something to remain from this talk, that any distribution with finite moments is either unique or it is non-unique. It all depends on the behavior of the higher order moments, or almost equivalently, it depends on the tail or the tails of the distribution, or the tail of the density function. Sometimes we have uniqueness, sometimes we have non-uniqueness. There are some cases, I call this some risky phenomenon, when we use moments without being sure that the distribution we work with is unique. Okay, thank you again. And now I'm now ready to listen to your questions and to give some more comments if necessary. Thank you again.
Thank you very much.
Thank you, John. Thank you so much for this very nice talk. Are there some questions, please? Are there some questions, please? Nabil, can you hear me?
Yes, yes, I hear you, Wissam. Yes, I think everybody hear you. Okay.
Jordan, you mentioned that some people do statistics with moments, estimators, without knowing if the distribution they are handling is moment determinate. I will tell you that a lot of people are doing statistics with with moments, estimators based on moments, without knowing if the distribution, if the data they have comes from the distribution having moments. Or,
Look, it is they are doing this. It is their own risk.
Yes, of course.
Some people I know, even personally, some people. There is a colleague, Aldo Tagliani, University of Trento in Italy, and there is Professor Robert Natsakanov. He's in West Virginia, and after seeing their first papers on this topic, perhaps I warned them, and now they started. Every time they tell at the beginning, one of our basic assumption is that all distributions we work with are a priori assumed to be unique in terms of the moments. And then let us show, for example, at how by using the first n empirical moments, for example, how to write explicitly an estimator for the unknown distribution function or for the unknown density. And now everything is going correctly.
Maybe I have another question for you. Meanwhile, maybe some other people will ask something else. If you know, let assume X is positive, and you know that it's moment determinate. Are there any tools indicating that the power of X could be moment determinant?
Yes, but I explained this. I can.
Yes, you
So
give the example of the normal distribution.
Yeah,
but
the
is
answer
there
is
any general rule?
Yeah,
if you lower the power.
So the normal distribution was a very good illustration of all the techniques that we have in our hands. You remember there was one page, very compact conditions. And you try this, and you will succeed, and you will tell. And what is interesting, you find the so-called boundary up to which power you have uniqueness, and when you are losing the uniqueness, and if you take a larger power, then you have already non-uniqueness. So we can show this, and we can show that.
But my question maybe was in the reversed way. You know that X is moment determinate. Are there any indication that says that X to the power alpha smaller than 1 remains moment determinate?
This is we can use the same techniques, and if alpha is less than 1, look at it. We try. You are right, because maybe if we take negative, very small, let's see, even negative, then if there is a huge mass around 0 of X, then X negative power will push the values to minus or plus infinity. So we can follow all the techniques, all the ideas, and answer your question. But it is a good question, and we know the answer. But it needs some arguments, of course. And we need to write, and then to check this, and then tell them.
Okay, thank you. Are there some other questions, please?
Can I ask a question?
Oh, yeah, sure. Yeah, I'm listening.
Yes, Fathi.
Somebody wanted to ask a question.
I think He's disconnected.
The question didn't come.
Fathi, you can ask your question. You have a problem with the microphone.
With the microphone, maybe.
Is this okay? Is this good?
Yes.
Yeah, now I can hear you. So go.
Okay,
Yeah.
thanks. Would it be possible to extend some of these results to stochastic processes? How would you extend these conditions to recognize whether a stochastic process is determinate or non-determinate?
My immediate answer is yes. I have done something on this topic. I have a few results which are published, but there are still some new questions that are waiting at somebody to spend the time. And so the answer is yes. But surely stochastic processes as an object to study and to deal with is a little bit more complicated, and we have to work with the multi-dimensional distributions, and then to involve very essentially the marginals.
Yes, Martin, yes.
And because of this, the topic multivariate distributions and multivariate or multi-dimensional moment problems, I have given a special talk on this topic.
That's good. That's you can send the reference or something to Nabil.
Yeah, okay, I can maybe Wissam. You saw at the very beginning at my email address. You can write to me, and then I will reply, and I will send to you some papers.
Thank you. Thank you very much.
Okay,
Thank
good.
You. That's very nice. Very kind. Very kind. Thank you. Thanks.
Zoltan, could you please go back just by one page?
Let me see. I cannot. This one?
Perfect. Okay, just to make the link with the question, the previous question, because I'm quite new in this topic, are there examples of Levy processes, let's say XT, for which you have moment determinacy up to time t0, but not after?
Yeah, after that critical value, you don't have moments at all.
Yes.
Yeah, this.
No, the moments would be good for everybody.
Okay, yeah.
I mean, x at time 1 is moment determinate, and not x at time 2.
I think it is possible. Yes. It depends, but this topic is still there are no study on this.
Okay, perfect.
So there is what to do.
Okay, thank you.
Okay.
Are there other questions, please? Cyril Banderi wrote a question for you. Can you? He wanted to be sure about your definition of a double factorial, and what should be the support.
This one, yeah.
Yes.
Everything is correct. Yes.
No. He wants to be sure about the definition of the double factorial. Your definition.
No, this is the product of the odd numbers in an opposite order, starting from 6k minus 1. So this is, so we have Z power 3, and all this, we are looking for the moment of order 2k of this. And this is Z power 6k. And this is how this 6k minus 1 comes as a factorial, double factorial. And now by eta, I'm denoting this mysterious discrete random variable with such moments. And so I tried it in different methods and all these infinite systems. You remember the system like in, it is a little easier.
I think Jordan, I think the question was like, for example, what's double factorial of 5? Like, what's the definition of
double factorial? Double factorial of no, it is now double factorial is defined only for even integer, even positive integer numbers, and we start with the next. Here we have all the usual factorial, and on the next we have double factorial.
Can you go back to the previous slide, please?
Okay, this one?
Yes, okay.
Okay, good.
Your discrete random variable, the support the sum over j, it is for j in n or in z?
Look, whatever you find, I will be absolutely happy.
Okay.
I will be absolutely happy, any, because only in this case, I will be able to draw the complete picture.
Yes, if
because
you
now my
finite
picture,
order for k, it seems that the moments that the pj are converging to infinity, so it is kind of strongly suggesting that the, well, not easy to get some.
Look at now I'm showing it these numbers. So these are unknown values, and these are the unknown masses. And because of this, I'm telling that we have because k is running 1, 2 up to infinity, so we have infinitely many equations, but also we have twice infinity many unknowns. So now you understand that probably and there will be infinitely many solutions, and I want to write explicitly at least one. And it seems to me if we can write at least one, then we will be able to write many. So at any time our knowledge is quite limited, but we try today, we try tomorrow. This
something
person
is strange in this sum. Why it is not j to the k?
here?
Yes.
Okay, it doesn't work. Okay, it can. Now J is running. The summation is from 1 to infinity. You cannot take. You want xj to be equal to j.
Well, because for the classical definition of moments, so this is why this.
No, but my mysterious unknown variable is y, and my assumption is that there is this v, the values. The set of values is this. These are the values. If you find that the integer numbers are good for you, but if you put here j, look at the numbers. You try to find the sum. They will go to infinity, and you don't get this. So in some balanced way, these numbers and these numbers must be found such that, so this k is a positive integer and it is fixed. And now we wanted running this, multiplying for any kind, and then we take it a k1, k2 to get the moments to be the same as the moments of power 3 of a standard exponential.
Jordan.
Oh, hello, Yasin. Hello.
Hello. So in fact, you have a Van der Monde matrix here. This
Okay,
is
we have, but I didn't go too far.
in fact, you can invert the relation and write the pj's in fact as a function of the moments and the xj's explicitly by writing the Fourier coefficient of some Lagrange interpolation polynomial at the
Okay,
x.
Okay, when during our next meeting with you, we will sit and write this.
Yeah, this what you have is a Lagrange interpolation, infinite Lagrange interpolation problem.
Yes, yes.
So you can try to find the xj's. So that's the Lagrange formula. So this is a sum of 3k factorials divided by x by z minus the xj. Xk.
Okay, we will try it. We will try this, but I'm glad that there are ideas. Yeah. Okay. Thanks.
You're welcome.
Is there any reason why you took 3 instead of 2 or 4 in this expression?
This is 3k because 3k factorial is exactly the moment of order k of power 3 of standard exponential. If I write here 2k factorial is exactly the moment of order k of c square. But c square, if 2k factorial, then we have uniqueness, which means that I can ask another question. If I write here 2k factorial, then I will show that there is no solution to this infinite system. And maybe what Yasin suggested that this Lagrange interpolation, some Fourier, some inversion, etc. Maybe this will help. And in one case, there will be no solution. In the other case, there will be infinitely many solutions. Here, now, instead of 3, I can write 4. Yeah, I can write 5. Because I know about any power of the exponential. So if we take this c and put this in power r, real number, if r is less or equal to, then we have uniqueness. If more than 2, we have non-uniqueness. So power 3, let me tell, maybe this will be useful. Power 3 is the minimal integer power of the exponential random variable c when we are losing the uniqueness. I believe now it is very clear to you why we try to play with this 3k. Because what is here as an open question, this is something missing. Yeah, look at it. So something more.
Okay. Are there any other questions, please? No. Then in this case, we all thank our speakers of today, Professor Jordan Stoyanov, and hopefully we'll hear you in another talk next year.
Thank you very much.
Okay, thanks again.
Thank
everybody.
you. Thank you, Jordan.
Okay. So is it time to close, to stop sharing and to leave the meeting?
Bye bye. Salam.
Okay, bye bye.
Okay, bye bye.
شاي طيبة نبي.
الشاي طيبة فتحي.
مش فارق إن شاء الله. السلام عليكم. سلام الله.
Bye.
Tu peux garder un tout petit peu, Nabil, juste un
Ok.
petit message et...